Hello and welcome. We, the students of SPIT EXTC second year, present a project titled Audio Compression and Analysis using Wavelet Transform in MATLAB. This MATLAB program provides a comprehensive, user-friendly graphical user interface for audio compression and quality analysis using wavelet transformation. This GUI allows users to load an audio file, visualize the original waveform, apply wavelet-based compression, and then compare the compressed signal with the original and display key metrics. These metrics provide insight into the quality loss and efficiency of the compression, making this application an educational and practical tool for audio and signal processing and evaluation. First part of the MATLAB code defines a MATLAB GUI script for an audio compression tool that includes functions to load and compress the audio. So in the first line, we define a function named audio compression, which accepts a variable number of inputs and outputs a variable number of outputs. This stands for variable argument out, and this stands for variable argument in. Now, these are a cell array which make the function flexible in terms of data inputs and returns. Next, we begin with the initialization of the code. The function UI figure is a function for creating modern UI figures in MATLAB. Using UI figure, we create a window which is named as audio compression. Next, using UI axis, we create a UI axis for displaying the original audio signal, which is positioned at x is equals to 50, y is equals to 300, and with the dimensions of 300 into 200 pixels. Another UI axis for displaying the compressed audio signal is defined and is positioned at x is equals to 400 and y is equals to 300. Next, we define labels using the function UI label for displaying metrics. Now, the first label is created, which is named as LBL size original, to display the original audio file size, and its position is specified with dimensions, and the initial text is set to original size. Another label named as LBL size compressed is defined to show the compressed audio file size. Its position is defined as well, and its initial text is set to compressed size. LBL PSNR label, which is used to display the peak signal to noise ratio, which is called as the PSNR value, which measures the quality of the compressed audio. It is basically the ratio between the max possible power of the signal and the power of the corrupting noise. Now, the next label that is defined is LBL MSE, which shows the mean squared error MSE value, which is another metric for measuring audio compression quality. It is positioned at x is equals to 50 and y is equals to 160 with the text as MSE. Next label is called as LBL compression ratio label, which will display the compression ratio, which indicates how much the audio file size was reduced to. Now, next we have is buttons for user interaction. The function UI button is used to define buttons. Now, the first one is BTN load, which is labeled as load audio, and its position is specified. Now, this function, button pushed function, specifies the properties of the button, which define the functions that will execute when the button is clicked. @BTN event is an anonymous function. The sign defines the anonymous functions. Anonymous functions are simple, they are one line functions, and they're defined in line for callback functions. BTN comma event, these are the input arguments for the anonymous functions. Load audio callback. Now, this is the function within the anonymous function. When the button is clicked, MATLAB will call load audio callback function with the arguments figure AX1, LBL size original, which define the various properties. Compress does a similar job, that is, when the BTN compress is clicked, it triggers compress audio callback function passing the figure AX1, AX2, and it displays the various labels that are defined. Now, when you run this part of the code, you will find that an audio compression window is created. Next up, we have the load audio callback function. As I press the button of load audio on the GUI, the load audio callback function gets executed. This lets users load an audio file, analyze its properties like size, and plot its waveform on the GUI. This function takes in three inputs: figure, the main GUI figure where data and settings are stored; AX1,
an access object in the GUI where audio waveform will be plotted, and label size original, a label where the original file size of the audio will be displayed. Next, we open a file dialog for audio selection. This line opens a file selection dialog, allowing the users to pick an audio file with a .wav extension. The UI getFile function returns two values. First, path, which is the directory path where file is located, and second, file, which is the name of the selected file. Let us see how it looks on the GUI. As I press the button of Load Audio, a dialog box is opened. Here I can select an audio file with a .wav extension and open it. A waveform gets loaded and is ready for compression. However, if I press the button of Cancel on the dialog box, the UI getFile returns 0 as the file value. The if statement checks for cancellation and exits the function immediately to prevent further processing. Next, we create a full path to audio file. This combines the path and the file name into a single variable, which is audio file path, which MATLAB needs to access the file. The full file function ensures compatibility across various operating systems. Next, we read the audio data. The audio read function loads the audio file's data, returning two values: x, which is the audio signal data array, which is basically the sound amplitude values over time, and fs, which is the sampling rate. The sampling rate, fs, is a key concept in digital audio. The number of samples of audio taken per second to represent the sound is called the sampling rate. It is usually measured in hertz. For example, a rate of 44,100 Hz, which is common in CDs, means that the audio is sampled for over 44,100 times per second. Higher sampling rates capture more detail, but they also increase the file size. For example, here you can see how increasing the sampling rate allows for a more accurate representation of the original sound wave and has improved quality of sound and reduced noise. The next line creates a time vector t for plotting. The length x minus 1 gives the number of samples, and dividing it by fs converts this count into seconds, making t represent the time corresponding to each audio sample in x. Next, we display the original file size. The dir audio file path gets data for the audio file, including its size in bytes. File info.bytes divided by 1024 converts this file size from bytes into kilobytes, and the next line updates the labels to display the file size. We usually store the uncompressed audio formats in .wav files. These store the raw audio data without any reduction in quality. These also have larger file sizes due to higher sampling rates and bit depths, which refers to the number of bits used to represent the amplitude values of an audio sample. For example, 16 or 24 bits per sample. This is ideal for professional audio work but not for storage efficiency. Here we have an flowchart which shows the compression process of a .wav file. Next, we plot the original audio. Plot ax1, t, x plots x, which is the audio data, against t, time, on x1, the axis for the waveform. We also create title, labels on the x and the y axis for better clarity. Lastly, we store data for later use. The set app data saves variables audio data x, sample rate fs, and audio file path in the main GUI figure. These can be accessed later when compressing the audio or computing metrics.
Continuing from what my teammate explained, I'll be justifying the final part of our code, which is the compress audio callback function. The compress audio callback function has various input parameters, namely figure axis 1, axis 2, label size original, label size compressed, label PSNR, label MSE, and label compression ratio. In the first part of the function, we retrieve the stored audio data, which is the audio data, the sample rate, and the audio file path of the original audio file. This is done using the getAppData function. for all the three variables. These variables are, as you might have noticed, these variables are redeclared. This is done so because the scope of these variables which are declared inside the function is that function only. And since these variables which were declared have been declared inside the load audio callback function, they cannot be used anywhere outside that function. As good practice, we also check if there has been an audio file loaded or not and display an error message for the same. Moving forward, here we check if the original audio file has only one channel or not. This is done by using the size function, which checks the dimensions of the X matrix is one is a single dimension or more or two dimensions. If so, it is converted into a mono channel by averaging the two channels. This is done by using the mean function. Coming to the main part of the code, we have the har wavelet transform, which is indicated by these three lines of code. The wavelet name is set to har. The level is set to 5, which indicates the depth of wavelet decomposition. The main transformation of the original audio file into discrete wavelets is done by using the wavelet function, which takes the following inputs, which namely audio data, the level of decomposition which is to be done, and the name of the wavelet, and returns the wavelet coefficients C and the length vector L as output. Now that we've performed the audio compression, we get to the part of the code where we only need to reconstruct the compressed audio and write the compressed audio into a new file. The reconstruction process is done by using the waverec function, which takes the inputs arguments as the wavelet coefficients C, the length vector L, and the wavelet name, which is har, and outputs the reconstructed audio data. This audio data matrix is now written into a new file by using the audio write function. This audio write function takes input arguments as the new file name, which is in this case compressed output.wav, the audio data which is compressed audio, and the sampling rate of the original file, which is same as the new compressed file. This part of the code is essentially the calculation of the compressed file size. This is done by getting the information about the compressed file first, then calculating the file size and by dividing it by 1024, which gives the file size in kilobytes, and updating the same on the GUI for the user to see. This specific set of commands is essentially plotting the compressed audio on axis 2 with their appropriate labels and titles, the title being compressed audio, X label being time, and Y label being amplitude. This line of code here is essentially the time range for which the function is to be plotted. The length of the compressed audio -1 represents the sample in the audio file by its index. The sampling frequency fs is measured in hertz, which means that 1 upon fs gives the time interval between two consecutive samples. Dividing the array 0 to length compressed audio -1 by fs converts the sampling indices into its time equivalents. This results in an array 0, 1 upon fs, 2 upon fs, to length of the compressed audio -1 upon fs, which represents the time at which each sample in the compressed audio matrix occurs. This part of the code is essentially the quality metrics calculations, which help us assess the trade-off between the compression and the audio quality. These are namely the MSE, the mean square error, the PSNR, the peak signal noise ratio, and the compression ratio. The MSE is essentially the quantification of the error due to lossy compression. The PSNR, the peak signal to noise ratio, provides an intuitive measure of the quality loss. And the compression ratio is essentially the ratio of the original file size upon the compressed file size, which shows us the degree of compression of between the two files. We've also updated the labels for these calculated values to be displayed and shown on the GUI for the user to see. This concludes our code. Now I'll be showing you a test run of our implemented code. On pressing the run button, we get the GUI designed for the code specifically. Um, Getting it to the center. Yeah. So on this graph specifically, we see the waveform of the original audio file. Loading up the audio file is an easy process. All you have to do is press the load button here, which gives me a prompt to select and load up the audio file. I'll be loading up the Windows XP startup file, which I have downloaded already. As we can see, the waveform is not a mono channel, but a stereo channel audio file, which can be seen from the green and blue waveforms. On pressing the compress button, we see the compressed audio file, which is a mono channel audio file. And as the requirement was, we have compressed the file size from 414 kilobytes to 207 kilobytes, which the given PSNR is 318.0602, and the MSE for the same is 2.34 e power minus 33. The compression ratio is almost comes out to be 2, which indicates that the size of the output audio file is half the original audio file. This concludes the test run of the implemented code. Thank you so much. Thank you for tuning into the video. If you've enjoyed it, please leave a like on it, and any comments or doubts regarding the video can be done in the comment section below on YouTube.